In module 4, we have learnt about ordinary differential equations. We have learnt about the different types of ordinary differential equations, and we learnt a little bit about first order differential equations. So, this is the 5th lecture of module 4, and in this lecture I will recap some of the things you have already learnt in this module and then work out a few practice problems. So, let us start with a recap. So, in module 5, in the first lecture you learnt the types of differential equations and the types of solutions. We learnt about linear, non-linear, homogeneous, non-homogeneous. We learnt about the order and degree of differential equations. Then in the second lecture we learnt about first order ODEs and how you can solve them using separation of variables, exact integrals and integrating factors. Then in the third lecture we learnt how to deal with a system of first order ODEs, okay, and how matrix methods can be used. And in the fourth lecture we explicitly solve the system of first order ODEs by solving the eigenvalue eigenvector problem and writing the general solution. Now, this material is you can find in the reference book. So, Macquarie has it in chapter 11, Kreyszig has it in chapter 1, but once again let me emphasize that I am not exactly following these books, okay. I am taking some content from this, and so you really have to follow the lectures and then try to follow the similar material in the books. Let us work out a few practice problems, and let me emphasize right here that differential equations are a part and parcel of all modern science and engineering. So, you can find them almost anywhere you look, okay. So, in chemistry you see them explicitly in areas like quantum mechanics, and in or in chemical kinetics or spectroscopy and so on, or any rate process will have a rate equation, okay, which will be in the form of a time derivative. So, it is not uncommon to find it, but also you might find it if you are trying to solve any mechanical problem, any problem in mechanics like a ball falling, okay, that will have a differential equation. I do not need to explicitly say where you use differential equations, since they are so widely used, okay, but during the examples I will try to take certain examples which will be familiar to you from your various courses. So, let us go. The first practice problem that I want to do has to do with classifying ODEs. Now, this is a fairly useful skill to have. I mean, many times it is not done explicitly, but I like to emphasize this part a little bit, so that you actually think before you rush to solving a differential equation. What I have asked you to do is to find the order and degree of each equation below, each ODE. When I say equation, I mean ODE. Classify as homogeneous, non-homogeneous, linear or non-linear. So, the first equation, written the differential equation, L times di by dt plus I times R is E0. This is an equation that comes when you are dealing with a inductor resistor circuit, okay, a very basic inductor resistor circuit, a battery, inductor and resistor. And the current when you just connect this battery, then the current follows this law. The current builds up over time and it follows this equation. Now, if you just look at this equation, the highest derivative that appears is the first derivative. So, it is a first order ODE. Now, the power of the highest derivative is 1. So, it is first degree. Okay. Now, this has each of the terms contains I or its derivatives to the first power or 0th power. So, it is a linear ODE. And we notice that the term on the right does not contain any I. So, the first term contains di by dt, second term contains I, third term on the right does not contain I or di by dt or d square I by dt or any derivative of I. So, it is a non-homogeneous equation. Okay. So, these are the characteristics of this equation, and you can solve this using the usual method of integrating factors. The next equation Okay. This m times dV by dt equal to m times g minus gamma times v. So, v is the dependent variable, v is the variable that depends on t, and this is the equation for some mass falling under gravity, okay, but it also experiences some air resistance. Okay, so, this gamma is a constant which tells you how much air resistance it feels, and the air resistance is proportional to the velocity. So, now clearly this is again a first order, first degree, it is linear, non-homogeneous. ODE. So, just like the previous equation, in fact these two equations are essentially identical. Okay, so, it is just different names for the constants, but essentially they are identical. Okay. Again this is a very important skill to have. We will see that the same form of the equation appears in many different areas. Okay. So, the first order differential equation, linear homogeneous first order differential equations, again that appears in several different contexts. Okay. In fact, in both these cases we had constant coefficients. Okay. So, the solution will be related to exponential, and again we see exponentials appear in different areas. Now, the next equation, okay, this I have written as dx by dt is b minus d, b and d are constants x, and m minus k x square. Okay. Now, I wrote this explicitly in terms of b minus d. I could combine b minus d into a single constant and m minus k into a single constant. So, I can just write this as a x plus b x square. Okay, but I explicitly wrote it in this way because such equations appear in population dynamics. So, for example, if x is a population of some species, okay, then the dx by dt, okay, has a birth rate. Now, the birth rate depends on the population that is there, okay, and a death rate, again that is also proportional to the population that is there. So, this is like the net birth rate of the species. Both of these are proportional to x. So, you cannot have a species born unless there is some species to give birth. Okay. Then there are other things that affect, this is I wrote it as m minus k. So, it could be that two species meet each other and they mate. Okay. So, m would be, that would lead to increase in population, okay, but that requires two species to meet. So, it is a x square term, but it could also be that two species could meet and just kill each other. Okay. So, there would be a that would lead to decrease in population. So, now such equations appear very often in you will see them in population dynamics, okay, and this is a fairly active area of research, and you know it is, I mean even though we have written it like a population dynamics, it is, such equations are often used even to model chemical equations. So, now what would this equation be? Clearly this is first order, first degree, and it is non-linear because there is an x square term, and it is non-homogeneous. Okay. So, this is an example of a nonlinear equation. We'll actually explicitly discuss nonlinear equations in more detail. Next is another the fourth equation that I have given is minus h bar square by 2 m d square by dx square of psi of x is half k x square psi of x plus plus half k x square psi of x is equal to e times psi of x. Now, this is a equation for a quantum harmonic oscillator. Okay, you see it very often in I mean you will see it in your quantum mechanics course. If you have not already seen it, you will definitely see it. Okay. Now this I have written it as an ordinary differential equation with a single variable. Okay. Now, the independent variable is x and the dependent variable is psi, is denoted by psi. Psi is the symbol that is used for the wave function. Okay. And so now what we have here is, as you can see, there is a term that involves the second derivative. So, this term involves the second derivative. So, it is a second order, and the second derivative is to first power. So, it is a first degree. Now, each term contains psi to 1 power. Okay. It contains either psi to 1 power or a derivative of psi to 1 power. So, it is a homogeneous and it is linear. Okay. And in fact, the linearity of the quantum mechanical equations are very essential for the very foundations of quantum mechanics. Okay. So, the fact that your Schrodinger equation is a linear equation is a very important aspect of quantum mechanics. Okay. And his equation is homogeneous. So, there is no term that is independent of psi, and that is also another feature of quantum mechanics. Okay. And in fact the fact that it is homogeneous and linear allows us to use matrix methods, okay, in quantum mechanics. Okay. So, that was about classifying ODEs. Now, let us go to the next problem. Okay. So, this is a the problem that is often discussed in certain textbooks. Okay. And I just wanted to take an equation. Okay. I have written this equation in this form: dy by dx is some function of x, p of x times y, okay, plus dy by dx plus p of x times y is equal to q of x. Okay. And you have to, and I am asking you to write the solution of this ODE in terms of one dimensional integrals over x. Okay. The reason the solution appears in terms of integrals is because I want to do it for an arbitrary p of x and q of x. Okay. Now, many textbooks do this as part of the solutions of differential equations. Okay. And so but since we did not explicitly do this, I thought we can work this out. Okay. Now, what we will do is we will write this in a familiar form. So, we will write dy plus p times y minus q dx equal to 0. So, I just rewrote this. I am not writing the dependence on x explicitly. Okay. So, now this is you can do the derivatives. Okay. So, if you take so this is n, this is m, n is equal to 1, m is this whole thing. So, you can clearly see that dou m by dou y minus dou n by dou x. Okay. Dou n by dou x is 0, dou m by dou y is not 0, is equal to p of x. Okay. So, we can see that that if I take this and I divide by n, 1 over n dou n by dou x, okay, n is just 1. Okay. So, this equal to p of x, this is independent of y. So, it is a function only of x. Okay. So, we can find r of x, that is integrating factor depending only on x. So, we can find an integrating factor that depends only on x, and let us write this. So, we will get r dy plus r p y minus q dx equal to 0. Okay. And what are the conditions? So, we should have this condition that when I take the derivative with respect to x, so I get dou r by dou x should be equal to derivative with respect to y of this, that is r times p, or you get I should write partial derivative, I should write dr by dx equal to rp, okay, because r is a function only of x. Okay, so this is an ordinary differential equation in x, and so what I can do is I can take the r to the left, I will get natural log of r is equal to p is integral p dx, or r is equal to e raised to integral p dx. Okay, I am not writing p of x, okay, this is integral p dx. So I did not write the constant of integration, I do not need to write it when I am doing this, when I will put the constants right at the end of the, when we finally solve the differential equation. So we got our integrating factor, and it comes as a one dimensional integral. If you know p of x, you can evaluate this r. Okay. So now once we have the integrating factor, we have to still solve the equation. So now our equation has this form where we know the value of r. Okay. So now let's so what we have is dou by dou x of this quantity r times p y minus q should be equal to or rather this should be equal to dou u by dou x, where this whole thing is du, it is an exact differential. So we call this du. Okay. So now what do we get? So let's do this integral, and what we will find is that u is equal to, so when you integrate this, what you will get is, in the first term I will take the y outside. So I will get y times integral r p dx, okay, minus integral r q dx. Okay, so this is u if I integrate it. Now it is a partial derivative, so I have a constant of integration, that constant will be a function of y. So I will say f of y. Now how do I solve for f of y? I say that dou u by dou y is equal to, so if I take the derivative with respect to y, okay, then in this term the y is there only here. So I will get integral r p dx, okay, and then I will have a minus, this term is independent of y, so that term does not contribute. So plus dou f or df by dy. Okay, so this is dou u by dou y, and this should be equal to r. So now I can integrate and I can get f equal to r y minus y, this is only a function of x. So it is y, so when I integrate it, I will get y multiplied by this whole thing, y times integral r p dx, that is my f. Okay. And now I can substitute in the expression for u. So what I will get is, now when I substitute this, this y times integral r p dx will just cancel here. So what I will get is u is equal to r y minus integral r q dx, and the solution is that this equal to constant. Okay, so now I can write the solution. I can take this to the right. I can write this implies y is equal to constant by r plus 1 over r integral r q dx. Okay, where r itself is this integral. Okay, so this is the final solution. So r is this integral, and your y is written in terms of r in this form. Okay. Now this is a very common, I mean this problem is actually very commonly seen. Okay. If I write this out, okay, so I will just write this out, okay, just to, so the first term, okay, looks like c divided by r, so that is e to the minus integral p dx. Okay. So this is the solution that would have been there if q was 0. If q was not there, okay, then you would just get dy by y is minus p dx. Okay, and so when you integrate it, you will just get this term constant times e to the minus integral p dx. Okay. So let me just write this. Okay, in this form. So, the first term is constant times e to the minus integral p dx. Okay, so, that is the first term. The second term is again you have e to the minus integral p dx from the 1 by r, and then you have integral of, now you have r itself is an integral e raised to p, r itself is e raised to integral p dx, okay, and you have q dx. So, these two terms look like this, and sometimes many books often give this directly as an expression to solve this differential equation. Now, what is important about this differential equation is that if q of x is not there, then this will be a homogeneous differential equation. Okay. So, what we did is so the first term is like solving the homogeneous differential equation. So, first you solve the homogeneous differential equation, then this is the solution due to the non-homogeneous part. So, the last problem that I want to do has to do with chemical kinetics, okay, and I just gave a very simple chemical kinetic scheme, okay, where I have A going to B with K1 and K2 and B going to C. Okay. So, this problem has three parts. So, first you write differential equations for concentrations of A, B and C. So, we can see this. So, if we call I will say instead of writing A is the concentration of A. So, this is concentration of A and similarly for B and C. So, this is the usual notation. Okay. And now, what we want to do is we want to write differential equations for this. So, what you will write is dA by dt is equal to minus K1 A. So, K1 A is the rate at which A disappears, and A is formed with a rate of K2 B. Now, dB by dt is equal to, now B is so it will be plus K1 A minus K2 B minus K3 B. Okay. So, I can write this as plus K1 A minus K2 plus K3 B, and then dC by dt equal to K3 B. Okay. So, these are the differential equations, and you can see that each of these is a first order linear differential. So, what we have is a system of first order ODEs with first order of linear. So, this is a linear system of first order ODEs with constant coefficients. And when you have such a system, you know that you can solve it using matrix methods. Okay. So, let us go ahead and write the matrix. Okay. So, I will call the C matrix. Okay. So, C is equal to A, B, C. Okay. Now, I can write dC by dt. Okay. So, C is a vector. So, C vector. So, dC by dt is equal to, now I will put this, I will write this matrix. Now, what is this matrix? So, this matrix you have minus K1 and you have plus K2 and 0. Okay. So, that comes from this equation. So, minus K1A plus K2B and 0 times C. Then you have in this case you have plus K1, you have minus of K2 plus K3 and you have 0, and here you have 0 K3 0. So, this is the matrix that you have, and now now you can try to calculate the eigenvalues and eigenvectors of this matrix. When you try to solve it, okay, we are given certain values, you are given k 1 equal to 4, k 2 equal to 2 and k 3 equal to 1. So, what you get is minus 4, k 2 equal to 2, 0, plus 4, minus 3, 0, 0 or 1, 0. So, now if you want to solve this, okay, so we need to find the eigenvalues and eigenvectors of this matrix. Let us solve for the eigenvalues and eigenvectors of this. Now to solve for the eigenvalues, what you will write is minus 4 minus lambda 2 0 4 minus 3 minus lambda 0 0 1 minus lambda, this determinant, okay, is equal to 0. Okay. Now if I evaluate this determinant, what I will get is this is minus 4 minus lambda times minus 3 minus lambda times minus lambda, okay, and then you have minus 1, and then you have plus 2 into 0 minus or 0 plus 4 lambda, and then you have 0 for the from the third term. Okay. So, what you get is you will get 4 plus lambda into lambda into 3 plus lambda plus 8 lambda. Okay. So, what I can take lambda as constant. So, lambda outside, and I can write it as 8 minus 4 plus lambda into 3 plus lambda, and so you need to set this equal to 0. So, you need to solve this equation. Okay. Now so either lambda equal to 0 or 8 minus, now we will expand this out. So, lambda square plus 7 lambda plus 12 equal to 0. So, I can write this as lambda square plus 7 lambda and plus 4 equal to 0. So, what you get is lambda equal to minus 7 plus or minus square root of 49 minus 4 into 4 16 divided by 2. Okay. So, you get so 49 minus 16 is 33. So, you get minus 7 plus root 33 by 2 or minus 7 minus root 33 by 2. Okay. So, we have the 3 values of lambda. Okay. So, we get lambda equal to 0. So, 0 or minus 7 plus root 33 by 2 or minus 7 minus root 33 by 2. Okay. Now, for each of these you have to find the corresponding eigenvectors. Okay. Now, if lambda equal to 0, okay, you can just see from this expression. Okay. So, if I take this and multiply it by 0 0 1, okay, so I will get with eigenvector. So, corresponding to this, the eigenvector is so if you write our equation minus 4 2 0 4 minus 3 0 0 1 0 times some I will just call it x 1 x 2 x 3 equal to 0 0 0. Then this can only be true if so implies x 1 equal to x 2 equal to 0 and x 3 can be arbitrary. Set equal to 1. So since we can choose it arbitrary, we will just set it equal to 1. So therefore, this eigenvector has the form 0 0 1. Okay. Now the next eigenvector. Okay. So suppose you have to solve for this. Okay. So suppose you have to solve for the next equation. So you will say minus 4 2 0 4 minus 3 0 0 1 0 times x 1 x 2 x 3 is equal to I will say minus 7 plus root 33 by 2 times x 1 x 2 x 3. Okay. So this implies minus 4 x 1 plus 2 x 2 is equal to minus 7 plus root 33 by 2 x 1. So, that is from the first term. The second, the second one gives you 4 x 1 minus 3 x 2 is equal to minus 7 plus root 33 by 2 x 2, and the third one gives you x 2 is equal to minus 7 plus root 33 by 2 root 33 minus 7 plus root 33 by 2 x 3. Okay. So, these are the three equations that you have. Okay. So, as you can see, the first two equations are will end up giving you essentially the same equation. Okay. So you can see that. Okay. So, the first equation gives you minus 4 or and the third equation connects x 2 and x 3. Okay. So, suppose you set x 3 equal to 1. This implies x 2 equal to minus 7 plus root 33 by 2 . Okay. And once you have the value of x 2, okay, so twice x 2 is just minus 7 plus root 33 by 2. Okay. So you can work out the answer to this to the value of x 1. Okay. So suppose you use the first equation, you get minus 4 x 1 plus or minus 7 plus root 33 by 2 x 1. Okay. So, I just took this to the left hand side, minus 4 minus this equal to minus 2 x 2. Okay. So let us just multiply this out. So, you get minus 8 and now you will get plus 7 minus root 33 divided by 2 x 1 equal to 2 x 2 minus 2 x 2. So, this is, so I can write, so now what I see is minus 1 minus root 33. So, I will just write x 1 is equal to 4 x 2 divided by 1 plus root 33, okay. And this will give me x 1 equal to 4 times now if I substitute this value of x 2, okay, so I will get twice minus 7 plus root 33 divided by 1 plus root 33. Okay. So, this is the value of x 1. So, I have x 1, x 2 and x 3, and you can explicitly solve the so we have the eigenvector corresponding to this to x equal to minus 7 to the eigenvalue minus 7 plus root 33 by 2. So, corresponding to eigenvalue minus 7 plus root 33 by 2, eigenvector is, so we set x 3 equal to 1, we got x 2 as minus 7 plus root 33 divided by 2, okay. And this let me just write this out as minus 14 plus 2 root 33 divided by 1 plus root 33. So, minus 14 plus 2 root 33 divided by 1 plus root 33. Okay, so, this is the eigenvector. It looks a little complicated, okay, but really I mean you can easily put the values and you can write the numbers. Okay. So, similarly eigenvector corresponding to eigenvalue minus 7 minus root 33 by 2 can be calculated. Okay. So, this eigenvector I will just write the value, okay. So, corresponding to this, okay. So, the eigenvector will look very similar to this. I will just write down the value, I will write here. So, you will get 1 minus 7 minus root 33 by 2, okay, and you will get minus 14 minus 2 root 33 divided by 1 minus root 33. Okay. So, it look very similar with just the minus signs, and so now we have so we can write the general solution in terms of eigenvalues and eigenvectors. So, the general solution C is equal to, so the first eigenvector is this constant eigenvector. So, 0 0 1, so it is C 1 times 0 0 1. Okay. Now, you have e raised to 0 t, that is not there at all, and C 2 times, now I will just call this V 1 V 2 and V 3, or so this is my V 2, okay. So, eigenvector V 2, okay, which is essentially this is V 3, and you have e raised to so minus 7 plus root 33 by 2 t, and you have C 3 times, now I will have V 3 here, okay. I am not writing the values, and I have e raised to minus 7 minus root 33 by 2 t. Okay. And now if t equal to 0, so each of these quantities is negative. Okay. So each of these quantities is negative. Okay. So, when t equal to 0, this exponent will go to 0. Okay. So what will happen is that this term will become 1, so will this. Okay. So, when t equal to 0, so your c at 0 looks like c 1 times 0 0 1 plus c 2 times v 2 plus c 3 times v 3. Okay. And what you will get is you will get 3 equations. Oh, so now this c 1 at 0 from the boundary conditions, this is basically 1 0 0. Okay. So, this gives you 3 equations for c 1, c 2, c 3, and we can calculate. Can be calculated. Okay. So finally, you can calculate c 1, c 2, c 3, and so this comes from the initial condition. So, initial condition we said that A has 1, B and 0 are 0. Okay. So, that was this initial condition. So, C of 0 has this form 1 0 0. You can get 3 equations and you can solve for C 1, C 2, C 3. Okay. So this gives the particular solution. And I am not actually explicitly working out these numbers, but you can substitute the values of V 1, V 2, V 3 and you can work it out. Okay. It will look a little messy because of these square root of 33. Okay. But essentially what I have shown is you can write the particular solution. Okay. So, once you have C 1, C 2, C 3, you know the solution of this kinetic equation. Okay. So what you got by this procedure is we did not apply any steady state approximation, we did not apply any equilibrium approximation, okay, but we just solved the general problem of this, the general chemical kinetics with this with these rates. Okay. So this is a very important application, and you can do this for any number of equations. In this case, since everything was first order, okay, so the whole system of equations was linear. Now, if you had second order differential equations, then you cannot do this because you will get nonlinear equations. Okay. Since everything was first order, you could do with linear equations, you could use eigenvalues and eigenvectors and calculate the general solution of this equation. So with this I will conclude module 4, okay, and next we will start module 5, in which we start talking about second order differential equations. Thank you.